Welcome to my projectbazaar.com.
Yeah, let us discuss about the reducing pointing errors in free space optical communication links over turbulence with partially coherent Gaussian beam. Yeah, let us discuss about the abstract of the product. So, communication is the transfer of the information between two or more points that are not connected by an electrical conductor. So, the most common wireless technology uses radio, with radio waves distance can be short and such a few meters for television, or as far as thousands or even millions of kilometers on deep space radio communication. So, in this proposed work, we present a joint investigation of the effects or spatially, and that is would be partially coherent Gaussian beam and aperture averaging on the performance of free space optical communication. So, that is a FSO communication systems from an information of theory perspective. So in the view of a theoretical term model, so is proposed to determine the optimum beamwidth of a partially coherent beam, so that is a PCB, for maximizing the average channel capacity in FSO, so that is a free space optical communication links, subject to the atmosphere turbulence and pointing error, so that is a PEs. So while increasing the receiver aperture size can be considered as a simple approach to mitigate the PE, so that is called a pointing errors, we demonstrate that the PCB, so that is a partially coherent beam, exhibits a vastly contrasting characteristics under the different atmosphere channel condition, and also illustrate the importance of feasible beam with the optimization technique for achieving the maximum capacity. So in our major objective is to reducing the pointing error by using the FSO communication system. Yeah, let us discuss about the flow diagram of the process. This is the overall flow diagram. So in the program, equipped RA, so that is the resource allocation and the secondary uses and the estimation of capacity for each subcarrier. Every subcarrier is using for the capacity value, and then system model. So the overall system model, whatever it may be present, and then transmit power of constraint of secondary users. So in this particular process, the secondary user will be developed, and design of reconfigurable with various pointing directions. So whatever it may be, we will design that should be reconfigurable for the various pointing of the directions. And then state selection. So in the state selection process here, we are using the APSSS and FP, so that's access point, and then calculating the free space of the using the gaming algorithm, and assign subcarrier for secondary users of the process. So joint subcarrier algorithm is in its maximum capacity value is achieved, choose as the best subcarrier, finally calculate the performance analysis of the process. So in the system model process, we calculating here. In this system model, the proposed model consists on one primary base station, that is a PBS, and multiple SBS, in which the primary users and secondary users are allocated randomly. So here the secondary users are equipped with resource allocation, which having the capability of choosing an antenna state among available possible states. So the omnidirectional antennas are mounted of the primary users and the PBS and SBS, whereas the secondary users use the random access within the game structure. So system also used orthogonal frequency division multiplexing approach, where the subcarriers are assigned for the secondary users. So the capacity of user at every subcarrier has been estimated where consider interference caused by the received signal from the jth SU on the kth subcarrier, transmitter power, and also calculating the channel gain of the process. So whatever it may be, they assign the secondary user or primary user, check whether the capacity values are high to reducing the pointing error of the process. So overall performance, finally we calculating the bit error rate reduction, and then actually calculated the value of whatever it may be, so reducing the pointing errors or like that. And then state selection is APSS or FPSS, whatever it may be, we only selected the APS algorithm or FPS algorithm, that is for the gaming algorithm, and then assign the subcarrier for secondary uses. Each subcarrier we selecting the assign the subcarrier of the values, finally calculating of the process. So these are the overall flow diagram of the process. Yeah, let us discuss about the running procedure for the process. So click the main file and then run. So enter the same process, it should be enter the value of 64, and then block size is I will selected 8. So enter the block size and the value of the process. So the reshaping modeling, so whatever it may be, the calculating, and then first of all the transmitted the input data. So then OIDM signal is processing. First of all, generating randomly input data, so the data points and the transmitted data represented the data, and then the modulator transmitted data. Here we're using the modulation is QAM. So by using the quadrature amplitude modulation, here we're shifting the points of data points, transmitted, modulated data, transmitted data. We're using the value of to easily to transmit the input data of the process, and then the reshaping of the QAM modulation, it should be the value, it should be replaced for whatever it may be, the value should be calculated. And then the OFDM signal process. So in the OFDM signal process, we'll be calculating the randomly input data, and then it should be modulated, and then finally calculating the OFDM signal by using the time and amplitude of the process. So that is the OFDM signal will represent the process. And then the next figure, by calculating the average electrical SNR and then average capacity. So in the average electrical SNR, we calculate optimization, RS and BES. So average whatever calculating the SNR, that is a signal to noise ratio, while calculating the average capacity of the process. So this figure is represented just like that, and then capacity level performance. So all the values which should be displayed, that is optimization scheme, RS scheme and BES scheme. So these are the different type of values which should be calculated. And then the next figure, so while transferring the data, so in this figure the average electrical SNR, the same process for the average capacity, so that value is displayed in the values of capacity level performance. And then in another figure, so that is the iteration index, in 0 to 40 iteration, what is the mean capacity value, so for RS and omnidirectional pattern. So that value is displayed in this mean capacity performance of the process. And the next figure, so in this next figure, the capacity level 0 to 30 capacity level, and then how much SNR, that should be the signal to noise ratio, it will be presented in this figure of the process. And then CDF response, so whatever may be calculated in the previous figure of the process. And another figure, calculating the AV electrical SNR for the particular capacity level for 0 to 25, what capacity value it should be achieved for the AV electrical SNR of the process. And then figure 15, number of secondary users. So number of secondary users are 20 to 60 secondary users. Total number of capacity, what it should be but be calculated for the process for assigning the secondary users. And then beam width, finally calculating the beam width of the process for proposed and existing algorithm for the normalized jitter. So normalized jitter is calculating 9 to 13.5 for the beam width, whatever it may be beam width calculated for 0 to 180 of the degree. So beam width means it represented in the degree, so calculating the degree of 0 to 180. So this is the final process, and then this value is calculating by using the RS algorithm and BS algorithm of the process. So and then finally calculating the values of 9 to 15, 9.7 and then 12.2, 11.9. So these are the overall running procedure for the product.
Thank you for listening this video.